Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss FRESNEL'S formulae for perpendicular and parallel polarization case. Let's begin. FRESNEL'S formulae, that is the equations relating the amplitudes of reflected and transmitted waves with that of incident wave are known as FRESNEL'S equation or FRESNEL'S formulae. The ratio of amplitude of reflected wave to that of incident wave is the first FRESNEL'S formula, and the ratio of transmitted wave to that of incident wave is the second FRESNEL'S formula. Here we derive the expressions as FRESNEL'S formulae in two cases. One is when E vector, electric field vector, is perpendicular to the plane of incidence, and another case when E vector is parallel to the plane of incidence. In that of two cases, derive two equations. These two equations are nothing but FRESNEL'S equations or FRESNEL'S formulae. Case number 1, when E vector is perpendicular to the plane of incidence. Let us consider an interface. This is the interface. In coordinate system, we denote it as x and z axis. That the interface separating it into two medium. Here is medium 1. It has permeability mu 1, permittivity epsilon 1. Medium 2, permeability mu 2, permittivity epsilon 2. Electromagnetic wave is incident on that of interface. That incident wave is given as k I vector. At that of interface, since it is partially reflecting and partially transmitting, this one as reflected wave, that one as transmitted wave. This is the angle of incident theta I, angle of reflection theta r, angle of transmission theta t. As we consider, E vector is perpendicular to the plane of that incidence, that is the plane of incidence at that of x axis, as we say z is equal to 0. Since we consider electromagnetic wave, in case of electromagnetic wave in which electric field as well as magnetic field and both are perpendicular to that of direction of propagation, if we choose E vector is perpendicular to that of plane of incidence, that is the plane, Here we take E vector. The direction of E vector, here that dot sign indicating that E vector is perpendicular to that of plane of incidence, that E vector inside that of plane of the paper. Similarly, we relate E vector to that of S vector, which is perpendicular to that of E vector, since E vector is inward, which is perpendicular to that of plane of incidence. Again, S vector is related to E vector, as S vector and E vector are mutually perpendicular to each other. So, the direction of E vector as inward, it is denoted by that dot sign, and that one as the direction of S vector. For incident, we call it as HI. For E vector, for incident, EI. Same for reflected wave, this is ER, that is HR. Again, that of transmitted wave is ET, which is perpendicular to that of plane of incidence. This one is ST. Okay. First we relate what is the relation between that E vector and S vector. We know that B vector is equal to K cross E vector divided by omega. Omega is the angular frequency, K is the direction of propagation of wave. Here you know B vector is equal to mu H vector. That is why in place of B vector we write as H vector is equal to K vector cross E vector divided by mu omega. In place of K vector, its magnitude and direction, unit vector along that direction. This is the unit vector along that direction, n cap cross E vector divided by mu omega. What is the value of K? As you know that K is equal to omega by V. Therefore, omega by phase velocity V is given as 1 divided by under root of mu epsilon. So, here K is written as omega mu epsilon under root. In place of K we write omega mu epsilon under root into n cap cross E vector divided by mu omega. Omega cancelled out, under root of mu, here mu, that is written as epsilon divided by mu under root n cap cross E vector. This is the value of S vector. When we taking only the magnitude, as an expression for S vector, as we know, S naught into e to the power I k dot r minus omega t. Here S naught is the amplitude, since we consider the magnitude 1. So, S as written as SO. HO is equal to epsilon mu under root E O. This is an important relation in between S vector and E vector. That relation is used in upcoming equations. Okay. Let us come to that picture. As we use E vector is perpendicular to that of plane of incidence. Now, using the boundary condition for electric field vector, from the boundary condition for electric field vector, the tangential component of electric field is continuous throughout the media, that separating by an interface. Therefore, the tangential component at medium 1 of that of electric field is same as the tangential component of medium 2 of that of electric field. What is the tangential component of that of electric field at medium 1? As we consider only the magnitude parts, if we write the expression for E vector as E naught into e to the power I k dot r minus omega t, like this, and its tangential part, as we say, in case of that boundary conditions, the positions and times are independent. The term relating to position and time are equating. Therefore, the tangential component we consider only the magnitude terms. Here the magnitude terms for medium 1, that is incident wave and reflected wave. For medium 1, the tangential component of incident wave tangential plus reflected wave tangential. At medium 2, only transmitted wave. Tangential. Here we take the magnitude parts EI, incident electric field tangential component, at its magnitude part E naught I plus here E naught for reflected wave is equal to E naught for transmitted wave. That is an equation number 1. What be the tangential component of EI? As we say, E vector is perpendicular to that of plane of incident, that is nothing but the tangential component. It is the tangential component, the amplitude of that of electric field vectors. Next, boundary condition for S vector. Again, from the boundary condition for magnetic field vector, here the tangential component of magnetic field vector are continuous. S1t is equal to S2t. For medium 1, that is incident wave and reflected wave, the tangential component for incident, the tangential component for reflected. For medium 2, it is the tangential component that for transmitted wave. Look here, what is the tangential component of SI? This is HI vector. When we draw that of normal to that of incident wave propagation direction, that creates an angle of theta I. So, its tangential component nothing but SI cos theta I. Here SI cos theta I, and we choose the magnitude parts, that is H O I cos theta I. If we prefer that as negative, then when dealing with the tangential component for that of reflected wave, it is taken as positive, since that one is opposite to this one. Here I take negative sign for that. Similarly, for that of reflected, its tangential component angle as theta r. So, the tangential component of HR as SR cos theta r, as we taking the magnitude parts, that is H O R cos theta r. This is the amplitude, is equal to, for that of transmitted wave, this is the angle theta t. So, its tangential component ST cos theta t, that is same direction to that of this one. So, we prefer negative sign here, minus H amplitude as HO for transmitted wave cos theta t. As we say, theta I is equal to theta r, angle of incident is same as angle of reflection. In these two terms, we take common. First multiplying the negative sign, we have H O I cos theta I minus H O R cos theta I is equal to H O T cos theta t, or H O I minus H O R common cos theta I is equal to H O T cos of theta d. Okay. Next, what is SOI? We use the relation as S vector and E vector, the magnitude part, as SO is equal to under root of epsilon divided by mu into E naught. Here for SOI, incident wave in medium 1, that is epsilon 1 mu 1 under root amplitude EO for that of incident minus reflected wave again at medium 1 epsilon 1 mu 1 under root E over of cos theta I is equal to, here S O T, that is at medium 2 epsilon 2 mu 2 under root into E O T cos theta d, or common as epsilon 1 mu 1 under root E O I minus E O R cos theta I is equal to epsilon 2 mu 2 under root E O T cos theta d. Our aim is to calculate the ratio of amplitude of incident wave to that of reflected wave. That is why is equation number 2. We can use that equation to transform that equation number 1. Here do not say that is equation number 2, again it can be simplified. Again it is simplified. Or epsilon 1 mu 1 under root E O I E O R cos theta I is equal to mu 2 epsilon 2 divided by mu 2 under root, in place of E O T, look here, E O T is equal to E O I plus E O R, E O I plus E O R cos theta d. Now rearranging the terms of OI and EOR, the terms rearranging as OI as epsilon 1 mu 1 under root EOI cos theta I minus epsilon 2 mu 2 under root E OI cos theta t is equal to the negative term to this side epsilon 1 mu 1 under root E OR cos theta I plus epsilon 2 mu 2 under root E OR cos theta t or EOI as common epsilon 1 mu 1 under root cos theta I minus epsilon 2 mu 2 under root cos theta t. Here EOR as common epsilon 1 mu 1 under root cos theta I plus epsilon 2 mu 2 under root cos theta t. Our aim is to calculate the ratio of EOR to that of ratio of EOI, and this is for what condition? This is for perpendicular condition, when that electric field vector is perpendicular to the plane of that incident. So, EOR divided by EOI, therefore, epsilon 1 mu 1 under root cos theta I minus epsilon 2 mu 2 under root cos theta t divided by epsilon 1 mu 1 under root cos theta I plus epsilon 2 mu 2 under root cos theta t. Equation number 2, which is FRESNEL'S first equation, that is the amplitude of ratio of reflected wave to that of amplitude of incident wave, that much under that of perpendicular situation. Next, the amplitude of transmitted wave to that of amplitude of incident wave can be easily calculating by using also from the equation, from that equation EOI plus EOR is equal to EOT, taking only EOR. From the equation EOR, from the equation number as 1, from equation number 1 EOR is equal to EOT minus EOI. Therefore, equation here I relate it to an equation number. Let I use it as equation number A. Then instead of EOR, we can use EOT minus EOI, as we have to calculate the ratio of that amplitude of transmitted wave to that of incident wave. Anybody can use it in that way and finally get that answer, but for our simplicity we putting that in this way. So, we obtained in equation A as epsilon 1 mu 1 under root E y minus E o t E y in place of E over cos theta I is equal to epsilon 2 mu 2 under root E o t cos theta t, or simplifying the terms as mu 1 epsilon 1 divided by mu 1 under root E o y minus minus plus, that is 2 y minus E o t cos theta I is equal to epsilon 2 mu 2 under root E o t cos theta t, or epsilon 1 mu 1 under root 2 E o y cos theta I is equal to epsilon 2 mu 2 under root E o t cos theta t plus epsilon 1 mu 1 under root E o t cos theta I, the term to this side. Therefore, epsilon 1 mu 1 under root 2 E o y cos theta I is equal to E o t as common, epsilon 2 mu 2 under root cos theta t plus epsilon 1 mu 1 under root cos theta I. Our aim is to calculate what? The ratio of E o t to that of E o I at a what situation? That is at perpendicular situation. Therefore, 2 epsilon 1 mu 1 under root cos theta I divided by the term epsilon 2 mu 2 under root cos theta t plus epsilon 1 mu 1 under root cos theta I. In the second FRESNEL'S equation, which is FRESNEL'S second equation, that is the ratio of amplitude of the transmitted wave to that of incident wave, that much. So, here we show that case number 1, when E vector is perpendicular to the plane of incidence, first we relate S vector to that of E vector, then using that boundary condition of electric field vector, boundary condition for a magnetic field vector, as it is the tangential one. So, I simply write, since it is not the tangential one, so the tangential form of that S vector is written, and simplifying in that manner we obtain first FRESNEL'S equation, the ratio of amplitude of that reflected wave to that of incident wave, and similarly at that of case, the ratio of amplitude of transmitted wave to that of incident wave. Again, case number 2 can easily be studied in the similar manner. Case number 2, when E vector is parallel to that of plane of incidence, same manner we consider that interface medium 1, medium 2, incident wave, reflected wave, transmitted wave, but the situation here is E vector is parallel to that of plane of interface. So, E vector is parallel. Since E vector is parallel to that of plane of incidence, then ultimately S vector is perpendicular to that of E vector, which is perpendicular to that of plane of incidence. So, it is given by S vector and E vector. Then for reflected wave and transmitted wave, we use boundary condition for that of magnetic field vector on that interface. It is continuous throughout that of medium. Since E vector is parallel to that of plane of incidence, so H vector is perpendicular to that of plane of incidence, that H vector is nothing but the tangential component. So the tangential component as its amplitude terms SOY plus HOR is equal to HOT. Next boundary condition for electric field vector, but that electric field vector is parallel to that of plane of incidence. So we evaluate what be the tangential components. So the tangential component for EOI, its tangential component, the angle created as to that of normal theta I. So its tangential component EI cos theta I, EI cos theta I. Similarly, if it is positive, then another one is negative, that is EOR cos theta R for that of reflected wave. The angle created as theta R, its tangential component ER cos theta R, ER cos theta R, negative sign. Similarly, for that of transmitted wave, EOT cos theta T, its tangential component ET cos theta T, amplitude term as EOT cos theta T. Using that of relation, H is equal to under root of epsilon by mu into E. In that of expression, it will be changed to, in place of HOI, substitute that SOR, SOT, as we relate it S vector and E vector. Here EOT can be calculated as this one cos theta I divided by theta T. Now separating the terms relating to that of EOR and EOI, here we take common EOR, here we take common EOI, as our requirement is the ratio of EOR to that of EOI, that is that parallel situation. When E vector is parallel to that of plane of incidence, we obtain that term. We are taking LCM as cos theta T and cancelling to that of numerator to that of denominator side, and finally we obtain that equation, which is FRESNEL'S first equation, which is FRESNEL'S first equation under what situation? When E vector is parallel to that of plane of incidence. Next one, same manner we proceed, but a simple change. In that of equation number 2, we calculate EOR in terms of that one and putting that EOR in that of expression. So we obtain in that of expression, in place of OR we substitute that one, and separating the terms related to EOI and EOT, EOI and EOT. Our requirement is the ratio of EOT divided by EOI at that of parallel situation. Mathematically, we finally conclude that one, the ratio of EOT divided by EOI at parallel situation, which is FRESNEL'S second equation. Under that condition, when E vector is parallel to that of plane of incidence. So here with the help of this video lecture, we understand the concept of FRESNEL'S formulae for perpendicular and parallel polarization case. What is FRESNEL'S formulae? It has two equations. One is the amplitude of reflected wave to that of incident wave, and another one is the amplitude of transmitted wave to that of incident wave. First case number 1, when E vector is perpendicular to that of plane of incidence. This is first FRESNEL'S equation under that condition. This one is the second FRESNEL'S equation under that condition. Next condition, when E vector is parallel to that of plane of incident. In same fashion, we proceed and we obtain first FRESNEL'S equation at that situational condition, and finally second FRESNEL'S equation under that condition as E vector is parallel to that of plane of incidence. So, with this useful and informative notes, let me wind up the session. Thank you.